Is gonna talk about the anaerobic co-digestion issues, and here's the floor.
Thank you. Good morning. Again, my name is Douglas Curtis, and today I'll be presenting on anaerobic co-digestion of chicken litter with mixed cover crop or Jatropha curcas biomass. So, Alabama produces over 1 billion birds with approximately 2.8 billion annually in revenue. Alabama is ranked third in broiler production in the United States. Therefore, due to the immense amount of broiler production, litter is produced at an average of 15 million metric tons annually. Broiler litter is a production, therefore causing a growing issue in the disposal within this industry. However, the broiler litter could be used in anaerobic digestion through co-digestion. Co-digestion could be used with plant biomass to produce biogas, renewable electricity, as well as biofertilizer for organic growers and add value to the litter. Such plant biomass could be Jatropha curcas, or commonly just known as Jatropha, or winter cover crops. Jatropha is a tropical plant that does not grow in the southeast United States, while winter cover crops are widely used by farmers in rotation with their main crops to improve the soil health. Okay, so anaerobic digestion. It is a biochemical process in which complex biological materials are biodegradated by microorganisms under anaerobic conditions. Biogas, which is the production from this, is composed of mainly methane, carbon dioxide, as well as trace gases, which are negligible. Here we have a flow chart of anaerobic digestion, just based upon. You can use energy crops, manure, as well as food waste. And it goes through the process, goes into a digester along with an inoculum or activated sludge. There, the gas is desulfurized, where it can be used in gas boilers as well as in engines. And then the byproduct of the sludge can be used for fertilizer. So, co-digestion is a widely used method for multiple substrates that do not meet the criteria for optimal biogas production. 1 ton of chicken litter produces more than 5 million BTUs of biogas. And poultry litter typically has a low carbon to nitrogen ratio, approximately 8 to 10, while plant biomass typically have a high carbon to nitrogen ratio from 32 to 35. And the optimal ratio discussed then for carbon and nitrogen ratio for anaerobic digestion is primarily between 20 to 30. Here we have the chemical breakdown of anaerobic digestion, in which 2 organic materials for co-digestion are pre-treated, in which the carbohydrates then go through hydrolysis. There, monosaccharides, amino acids, and long-chain fatty acids are produced, in which acetogenesis comes in and therefore creates different acids. Next is acetogenesis, in which acetic acid, hydrogen, and carbon dioxide are produced. And in the final step of anaerobic digestion, there's methogenesis, in which methane and carbon dioxide are primarily produced. So the objective of this study was to assess the biochemical methane potential of Jatropha leaves and above ground cover crop mix in co-digestion along with broiler litter. The substrates used within this experiment were as follows: Jatropha leaves, chicken litter, and a mixture of above ground biomass of these cover crops of bruised rye, bell bean, black oak, crimson clover, hairy vetch, taproot radish, and winter barley. A subsample of the co-substrates biomass from the ratios were analyzed for total solids and volatile solids to be able to determine how much must go into each reactor. So the total solids is done by weight 4, which is the weight after the co-substrate has come out of the furnace at 500 degrees, and weight 1 is just the weight of the crucible. Weight 2 was the weight of the substrate in the crucible before any oven drying or burning, and weight 1 again was the crucible. Volatile solids, which is the percentage of total solids, was found through weight 3, which was the weight from the oven, subtracted by weight 4, which is the weight after the furnace, divided by, again, weight 3 and weight 1. There we took the total and volatile solids calculations and results and was able to determine the concentration of each of the inoculum as well as the substrate, which is just the total solids of each product times its volatile solids. Next, we had to calculate the amount of inoculum that would be going into each reactor bottle, which was done by taking the concentration, 800 minus the concentration of the substrate divided by the concentration of the inoculum plus 2 times the concentration of the substrate. There we were able to find the amount of inoculum that goes in. Next, we calculated the amount of substrate, which was just 400 minus the inoculum amount. So the cold substrates were weighed out in triplicates and added into the BMP reactors. Next, each reactor will receive the inoculum to approximately the value of 400 milliliters. The reactor bottles were then capped and nitrified to remove oxygen from the reactor, and the cold substrate and the inoculum were incubated in 30 days in a biomethane potential test using 2 PFA 1000A anaerobic respirators. Here we have the respirator, which you can see there are 2 water baths, as each water bath contains 8 reactor bottles. And at the top right, we have the heater pump, which provides the hot water to keep the temperature at 37 degrees Celsius for the reactor bottles. And then at the bottom right, we have our respirator, which is connected to carbon scrubbers to remove carbon dioxide gas. So here we have our first results, which our first test, we was just determining which ratio would be the optimal. And the ratios used were 0 to 1, Jatropha leads to chicken litter, 1 to 0, 1 to 1, 1 to 3, and 3 to 1. Here we found out that the leading producer within this graph was the Jatropha leaves chicken litter 1 to 3. Next, we did another setup for this experiment in which we increased the ratios, and we kept the ratio 1 to 0 of Jatropha leaves to chicken litter, but then we had ratios 1 to 4, 1 to 5, 1 to 10, and 1 to 20. Here we saw a decrease in biogas production compared to the first ratio, but the highest ratio produced within this one was the 1 to 10. Next, we have the actual values of the final numbers. Here it shows that, again, the highest one was Jatropha leads to chicken litter 1 to 3 ratio, in which, to ensure we got the exact number of how much biogas is just produced by the substrates, we subtracted the inoculum to make it void. And here we have the results from another test in which we used the above ground cover crop mix, in which the ratios were based upon the previous test, 1 to 4, 1 to 5, 1 to 10, and 1 to 20. Here it was even a lower decrease in biogas production, in which the highest one, again, was 1 to 10. And again, we did the same thing, in which we subtracted the inoculum just to see how much biogas produced mainly from the co-substrates, in which we see that the 1 to 10 produced the highest. Here we have the characterization charts in which we ran tests such as volatile acids, total alkalinity, and found the alkalinity to volatile acid ratios, in which we was doing this to see in the volatile acid to alkalinity ratio, there's a certain limit in which each one range was in the range, therefore providing us with the information saying that each reactor were healthy. Next, we did chemical assays on chemical oxygen demand and phosphorus. As you see, the chemical oxygen demand increased as the product went through incubation, while of course the phosphorus decreased as it was used by the microorganisms. From the results obtained, it was conclusive that the co-digestion of tuber crops and chicken litter is possible to achieve biogas production. The leading producer of biogas with co-digestion of Jatropha leaves to chicken litter was 1 to 3 at a rate of 19,887 milliliters, and above ground cover crop mix to chicken litter ratio 1 to 10, which produced a small amount of 10,909 milliliters. The co-digestion of Jatropha leaves 1 to 1 produced the least amount at 5,202.7 milliliters, and the mix produced the least at ratio 1 to 4 with an amount of 4,759 milliliters. The volatile acids to alkalinity ratios were within the range for the optimal biogas production. In conclusion, the experiment did show the offspring ratio for co-digestion was 1 to 3 of Jatropha leaves to chicken litter. Furthermore, chemical assays were only ran on the first run to determine errors in the testing, and secondly, human errors and malfunctioning machinery could have caused minimization of producing the biogas. Questions?